Hello everyone, welcome to my video. Big models like GPT are super popular in AI right now, with transformers at their core. Actually, the cover for this video was created using ChatGPT, a testament to the very technology we are discussing today, the transformer. Today, I'm going to show you how to make one using PyTorch. With PyTorch, it's easier than you might think to make a transformer. By the end of this guide, you will know the basics of how to build and use one. Before we dive into coding, let's quickly overview the landscape of transformer models. Transformers can be categorized into three main types based on their architecture and functionality. There are models that include both encoders and decoders, models with only encoders, and those with only decoders. Each serves distinct purpose in the AI field. Models with both encoder and decoders are typically used in tasks like language translation, where understanding context and generating appropriate response are equally important. Encoder-only models excel in understanding what a sentence means, like figuring out if a comment is happy or sad. BERT is a famous example of this. Conversely, decoder-only models specialize in generating text. They can make new sentences from just a little bit of information, like a prompt. GPT is a well-known model in this category, capable of producing human-like text. Now, let's start building a transformer model with PyTorch. I had a tough time finding clear instructions on how to set up, train, and use it effectively, so I decided to put together this guide to help everyone out. As usual, let's start by importing the necessary libraries in Python. In the transformer model, the order of input sequence isn't directly considered by its components, posing a potential challenge, as sentence meaning can vary significantly based on what order. For example, the cat catch the dog or the dog catch the cat. Let's dive into how to address this challenge using positional encoding. The concept is smart yet effective. Add distinct signals to each input token's embedding, changing in a set pattern by position. These signals are designed such that the model can determine the position of each token in a sequence, even when processed in parallel. This is achieved through the use of sine and cosine functions of different frequencies, enabling the model to distinguish between positions based on the unique combination of these signals. With this understanding, let's dive into how we can implement positional encoding in our model. We start by defining a class called positional encoding that inherits from an endpoint module. This class will handle the positional encoding logic for our transformer model. We define the constructor method init for our positional encoding class. It takes in parameters such as dimension of the model, dropout rate, and maximum length of input sequence. We then initialize the dropout layer. Dropout is a regularization technique that randomly sets a fraction of input units to 0 during training to prevent overfitting. Next, we create a positional encoding matrix, PE. We generate a vector representing the position of each element in the sequence using the formula. We calculate the divisor for the sine and cosine function used in positional encoding. We apply the sine and cosine functions to the positional encoding matrix, PE, according to the transformer positional encoding formula. We register the positional encoding matrix as a buffer to ensure it's included in the model state dictionary but not changed as a parameter. Finally, we define the forward method of the positional encoding class. It applies positional encoding to the input tensor X and returns the result after applying dropout. Now we are moving on to putting together our transformer model. This class transformer is where we integrate all the components into a functioning model. It's structured to handle the complexities of transforming input data into meaningful outputs using the transformer architecture. We initialize the class with a set of parameters, defining the model's architecture. Within the constructor, we first set up some basic attributes like model type and dimensionality. Then we get into the code components, the positional encoder that acts sequence awareness. The embedding layer that converts token IDs into vectors. The transformer block itself for processing. And finally, the output layer that maps the transformer's output back into our token space. In the forward method, we prepare our input data by applying embeddings and positional encodings. Then adjust the dimensions to match what the transformer block expects. We process the input through transformer. And the output is then passed through a linear layer to get our final prediction. This class encapsulates the core functionality of the transformer model, from input to output. It's a comprehensive setup that utilizes the transformer's parallel processing capability for efficient and effective learning and prediction. And there you have it. Despite the complexity it can handle, at its core, this model is quite straightforward to set up and use. Next up in our transformer model setup is tackling something called target masking. This might sound a bit abstract, so let's break it down into what it means for us coding these things. When our transformer is training to predict the next word in a sentence, we don't want it cheating by sneaking a peek at the answer. That's where target masking comes into play. It's like when you were in school, taking a text with your hand covering the next questions, so you couldn't jump ahead. We are essentially doing the same thing for our model. Here's how. First, we defined getTargetMask with a size argument. This size is how big the mask needs to be, based on the sequence length we are working with. Here, we create a square matrix of the given size filled with ones. Then use torch point trial to keep the lower triangle as 1 and set the upper triangle to zeros. It's a lower triangle matrix. This step ensures that for any given word in a sequence, the model can only look at it and the words before it, not after. We replace every zero in our matrix with minus infinity. During the attention calculation, this effectively masks out the model's attention to future token because the softmax of minus infinity goes to 0. Then we replace all the ones with 0.0. This is because in the attention mechanism, adding 0 doesn't affect the calculation, allowing the model to consider these positions. And finally, we returned our mask. This mask will be used during the forward pass of our model to make sure it only pays attention to the current and previous token in the sequence, not the future ones. Let's generate some random data for training our model. First, we define a function generate random data n, where n is the number of data points we want to generate. We set up special tokens for the start and end of our sequence. These tokens are used to indicate the beginning and end of a sentence to our model. We decide on a fixed length for our sequence. Here we are using 8 as our sequence length. Now we initialize an empty list to hold our data. Next, we generate 3 types of sequence to diversify our training data. The first type is sequence filled with ones, the second with zeros, and the third is alternating ones and zeros. This variety helps the model learn different patterns. For a sequence of ones, for a sequence of zeros, for alternating ones and zeros. After generating all our sequence, we shuffle the data to ensure the model is trained on a random order of data points. Now, onto batchified data, where we group our data into batches. This function takes our data and groups it into batches of a specified size. It also has an option to pad shorter sequence in each batch to ensure they are all the same length. We start by defining our function with parameters for the data, batch size, whether we want padding, and a padding token. We will iterate over our data in steps of batch size, grouping data points into batches. We check to make sure we don't create a batch that's smaller than our specified batch size. If padding is enabled, we find the longest sequence in the batch and pad the rest to match. After possibly pending, we add our batch to the list of batches. Once all batches are created, we print out how many batches we have and their size. Finally, we return our list of batches. To use this function, we generate our training and validation data, then benchify it. And that's it. We have prepared random data for training and validation, grouped into batches, ready for our transformer model. Now we are moving into setting up our environment and getting our transformer model ready for training. First, check if a GPU is available for training, as it significantly speeds up the process compared to using a CPU. If not available, default to CPU. Next, we initialize our transformer model with specific parameters. We are keeping it simple with a small number of tokens, model dimensions, heights, and layers. We also set a dropout rate to prevent overfitting. After creating the model, we send it to our device. Choose the stochastic gradient descent optimizer for adjusting the model parameters during training with a running rate of 0.01. This optimizer updates the model's weights to minimize the loss function. Define the loss function as cross entropy loss, which is commonly used for classification tasks. This function measures the difference between the predict output and the actual target, guiding the model to improve its prediction. Following these configurations, the model is equipped with an optimizer and a loss function, prepared for training on the chosen device. Now, we will concentrate on the training loop that fine-tunes our transformer model's parameter to better align with our data. The train loop function kicks off by switching the model into training mode. This is crucial, as it tells our model that it's time to learn. Dropout layers and batch normalization layers will operate as needed for training. We initialize a variable to check the cumulative loss over all batches within an epoch. This allows us to measure the model's progress in learning. Iterating through each batch provided by our data loader, we destruct each batch into input X and target Y sequence. These sequences are then converted into tensors and moved to the appropriate device to match the model's location. For the model to predict each token in the sequence without seeing the future tokens, we prepare Y input by excluding the last element of each target sequence and Y expected by removing the first element. A target mask is generated to ensure the model only uses the current and previously seen token to make prediction. This mask is also sent to the device. With our input, targets, and masks ready, we feed them into the model to get the prediction. This step is like promoting the model to complete the missing path given the initial elements. We compute the loss by comparing the model's predictions against the actual next token in the sequence. This difference gives us a measure of the model's current performance. Before we can update the model's weights based on the loss, we clear out any odd gradients, ensuring we don't mix gradients from previous iterations. Then, the loss is sent back through the model, calculating gradients for each parameter. With our gradients calculated, we take a step with the optimizer. Let's update the model's parameter in an attempt to reduce the loss. After processing all batches, the average loss across all batches is computed by dividing the total loss by the number of batches. This average loss is indicative of the model's performance over the entire dataset for the epoch. This process repeats over multiple epochs gradually improve the model's ability to predict the sequence of tokens, refining its parameters to better understand and generate the data it's trained on. We have got our chain loop function to set up and ready. Now, let's tweak this code to create our validation loop. First, we change the function name to validation loop. Next, we switch the model to evaluation mode by this. This tells PyTorch that we are not training anymore, so it should handle dropout and batch normalization differently. Now, wrap the entire for loop with torch point no grade. Inside the loop, our data handling remains the same. We are still preparing y input and y expected in the same way, because the model's input and output formats don't change between the training and validation. However, there is a subtle but significant difference in how we process each batch. Since we are evaluating, we skip the 3 steps. These are related to updating the model, which we don't do during validation. And that's it. We have taken our chain loop and adapted it into a validation loop. This updated function allows us to assess how well our model performs with new data, ensuring it's not merely adjusts to training set, but is truly learning patterns that apply broadly. Next, we are going to encapsulate the entire training and validation process within a single function called fit. First, we define this function. We are preparing to check our training and validation losses over time, storing them in this. This data will be valuable for analyzing the model's performance and improvement across epochs. Announce the beginning of the training and validation process. We enter a loop to iterate through each epoch, where an epoch represents one full pass through the entire training dataset. For each epoch, we run our chain loop with the current state of the model, optimizer, loss function, and the training data loader. The training loss for the epoch is then stored. Similarly, we run the validation loop. After both training and validation steps are complete for an epoch, we print the losses. These logs provide immediate feedback on the model's performance, showing whether it's improving and how it performs on ANSI data compared to the training set. Once all epochs are complete, the function returns the list of training and validation losses. This list can be used for further analysis. Finally, we call the fit function. This starts the entire training and validation process. Now, since the model is still under training, let's explore the function predict, which is an example of applying the model in a practical scenario. Then we initialize the output sequence with a SOS token. This signals the beginning of a new sequence for the model. We define a loop that will allow us to iteratively predict each token in a sequence until we reach a maximum length or the model predicts an EOS token. Within our loop, the first step involves generating a target mask. This mask prevents the model from looking ahead to future tokens, mimicking the training condition. Next, we make a prediction based on the current state of the input sequence and the target mask. The model outputs probabilities for the next token in the sequence. We then extract the token with the highest probability as our next item in the sequence. The predict token is appended to our input sequence, and this update sequence will be used in the next iteration of our loop. If the model predicts the EOS token, we break the loop, concluding our prediction phase. Let's see our prediction function in action with some examples. We loop through each example, invoking our predict function and then displaying the original sequence alongside the model's prediction. Let's stop the training process and make the prediction. Through this example, we have seen how the transformer model can be utilized for sequence prediction tasks. This look into transformers shows us the basis of how powerful these models can be handling for sequence, whether it's language, number, or any data that follows a pattern. It's a testament to how far we have come in teaching machines to understand and generate human-like text. Thanks for watching. I hope this gives you a good starting point for your projects with Transformer. See you next time.